In the last lecture, we looked at real inner product spaces. In a similar way, in this lecture, we're looking at real normed linear spaces. So when we covered inner product norm and metric on Euclidean space, we associated to the idea of the norm the measurement of length. So how long is a vector in Rn? To generalize this notion, imagine we have some vector space V. Our norm, which we will denote in a similar way to the vector norm, so just this kind of double bar symbol, is a real valued function on any vector from V, which is going to satisfy what we want it to do if we want to say how long an element from our vector space is. So let's think over what notions we associate to length. If I ask how long is my marker, it would be really strange for you to say -8 centimeters, right? So whenever we give a length, we usually give 0 or a positive number. That will be our first requirement, so let's call that positivity. For any element V or any vector V from our vector space, the norm of V is greater than or equal to 0. What has length 0? You would never say my marker has length 0. What has length 0? Really nothing. For a vector space, we'll call that the origin. So only the origin in a vector space has length 0. Everything else has positive length. Let's call that non-degeneracy. So this is 0 if and only if we are taking the norm of the 0 vector. I'm using traditional vector notation here, in part because I want to highlight the difference between the 0 vector and the scalar 0. So here, this 0 is just a measurement. This is just a real number length. And this is the origin in our vector space. Okay, our next property is this notion of scaling. So if I take a vector and I stretch it by a factor of 3, its norm should go up by a factor of 3. We'll call that multiplicativity. Multiplicativity. All right, so if I take a vector and scale it by some real number alpha, compute the length of that. Just be careful here that you don't write alpha times the length of V, because alpha could have been a negative scalar, and this would not look right if you compare it to positivity. You need to take the size of alpha. Okay, so that's the only place here where sometimes people get a little careless is when they pull scalars out front. Make sure you realize that you need the absolute value of that scalar, which is a good moment to mention that if we're looking at R, the vector space R, the Euclidean real number line, double bar symbol is really just absolute value. And if you are working on the real line, I encourage you to write absolute value and not the double bar notation, because that basically acknowledges that you're working in this special setting where our notion of length and size is just to take the absolute value. So if I see a student working on the real number line and they're using the norm notation, it makes me wonder if they recognize that the norm on Euclidean real line is just the absolute value function. Okay, so that's just a little aside there about that one special setting. Let's wrap up our list of properties here with the idea that the fastest way to get from point A to point B is just a straight line in the vector space. If you take any kind of detour, if anything, you're lengthening your travel. Okay, I'm just trying to say the triangle inequality. So the triangle inequality tells us that if I take two vectors and add them together, the norm of their sum is less than or equal to the sum of their norms. Take a moment to sketch a picture of this statement in R3. Or actually, your picture will be on R2 because it will be on a flat surface. So just take two vectors, V and W, do vector addition, and then identify in your picture what is this length versus what are these two lengths. All right, let's just draw a vector V. If I want to do vector addition with this and another vector W, I'm going to do it correctly where I put the tail of W at the head of V. So how about this is vector W. so that the vector sum v plus w goes from here to there. I'm going to stretch v out so that it looks like, okay, there we go. I had to correct my picture a little bit, but let's say it looks like that. Okay. So this is v plus w. All right, so v plus w is v plus w. And of course, now we see that if we took the length of this side and compared it to the sum of the length of this side with this side, that's the triangle inequality. So this is the shortest way to get from this point to this one. The shortest path is this direct path and not this detour. Okay, the goal for the rest of this lecture is to look at a few different norms because I think you've seen absolute value before. I hope so. You've seen vector norms before, so I would like to show you some others. And then I have a couple of results for us to examine. Let's start with the LP norms on Euclidean space. So imagine that we're working in Rn. We'll draw pictures in a moment in R2. So we have vectors, which I'm denoting here with this X notation in Rn, and I would like to compute a few different norms for them. For any p greater than or equal to 1, we have what's called the LP norm. What we do is we take each coordinate of the vector x and compute its size. So that's going to be like, leave yourself some space here, the size of the first coordinate to the pth power plus the size of the second coordinate to the pth power. Okay, I didn't say I was going to do it to the pth power, but that was coming. So take the size of each coordinate, raise that to the pth power, add all of them together, and then take that sum and raise it to the 1 over pth power. Okay, so that is the general expression for the LP norm, but I would like for you to take a moment and look at these first two examples. So here's the L1 and L2 norms. Just pause with this expression and clean it up so that instead of this p and 1 over p, we're looking at the specific best ways to write down the L1 and L2 norms. I asked you to work through both of these on your own. Let's stick with the L1 norm for a while. I'm going to build some exercises into this. When p equals 1, each of these powers is 1, including this one. So that the sum just becomes the size of x1 plus the size of x2, all the way through, adding to that the size of xn. Okay, so that's the L1 norm on Rn. Let's check the 4 properties of a norm for this. So these are the new exercises I'm throwing into this. We need to check, let's see, positivity, non-degeneracy, multiplicativity, and the triangle inequality. Okay, I think the first two we can just do out loud. This is the sum of absolute values. It's never going to be negative. Okay, so we have positivity here. For non-degeneracy, don't forget that it's an if and only if statement. So first, let's imagine that we compute the L1 norm of the origin. Each of these would be 0. Adding 0 to itself n times would give us 0. So the L1 norm of the origin is indeed 0. Going the other direction, what if we compute the L1 norm of a vector and we find that it's 0? Can we conclude that that vector must have been the origin? The answer is yes. So conversely, if this sum is 0, then because each of these terms is greater than or equal to 0, we must have added 0 to itself n times, which means each individual coordinate was 0, so that was the 0 vector. For multiplicativity, it's not hard, but I think it's got a few steps, so let me just write it down. It's all just algebra. Suppose we take the vector x and we scale it by the real number alpha and compute the L1 norm of that. Then alpha is just going to distribute to each of the coordinates of x. So this multiplication would look like alpha times each coordinate of x. That would mean that we would have alpha x1, I'm just going to say plus dot 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 through the size of alpha xn. I just want to emphasize here that when I pull the alpha in front, I need to recognize that it's the size of alpha. So the absolute value of this product is the product of their absolute values like this. Oops, I forgot to break it apart. Hang on. I was trying to write xn as nicely as possible, and I kind of forgot what I was doing. There we go. Okay, factor alpha in front, and we have alpha times the sum of the sizes of the individual coordinates. Like that, okay. But this, of course, is the L1 norm of the original vector x. All right, so that's what checking positivity would look like. Let me pause just for a moment so that you can write this down, I can erase it, and then we will just run through the triangle inequality for the L1 norm as well before moving on to the L2 norm. For the triangle inequality, let's take two vectors, add them together, and compute the L1 norm of that. Well, this vector addition is just pairwise adding together their coordinates so that this would look like the size of the sum of the first coordinate, so x1 plus y1, added to the size of the rest of them through xn plus yn. I'm assuming that we've already shown in first semester real analysis how absolute value behaves, because at that point, when you come into this class, you should have really worked through the Euclidean real line so that we know that the triangle inequality applies to each of these individual expressions. So this sum, the absolute value of this sum of real numbers is less than or equal to the sum of their individual absolute values. And then that's true for the rest of them. And then if you like, you could write one more line where you kind of gather the x's together, gather the y's together to say that this is the sum of the sizes of the x coordinates. So that's the L1 norm of x plus the same for y. All right. So the triangle inequality also holds. So that's just an example of testing the four norm properties for this one particular norm. We will do that again later with a different looking norm, but let's move on now. I'm going to take a moment to erase all of this before we talk about the L2 norm. For the L2 norm, each of these p terms will be 2, and this will be 1/2, which means that we are adding together a bunch of squares and then taking the square root. That should sound familiar. So I'm going to write this down now using that interpretation of this expression. Notice that if I am squaring each of these sizes, I don't need the absolute values anymore. So don't get so used to what I'm about to write down that you forget about these absolute values for the general expression. All right, so what is the L2 norm? It's going to be the square root of the size of x1 squared, which is equivalent to just x1 squared, plus same thing for x2, all the way through xn. Okay, so we've squared a bunch of sizes, but that's the same thing as just squaring the coordinates, added them together, raised them all to the 1/2 power is like taking the square root. Okay, so that should look familiar. This is the regular Euclidean norm. And if you're wondering if the first one also had a name, it does. So L1 norm is pretty standard, but you might also see this called the taxicab norm. For reasons that I will not go into until our lesson on metric spaces. I have another norm on the screen that fits into this family. So here if I write p is greater than or equal to 1, that expression usually means p is a finite number. But with this group, I'm going to throw in what's called the sup norm. Fits in, which will become clear in a moment. So just stick with me for now with the sup norm. But we will say that the sup norm of this vector x, which we denote as the norm of x with that subscript infinity power, so there it's kind of like we let p equal infinity. It's going to be the sup of the sizes of the coordinates. So it's a set supremum. You might be wondering why I wrote sup. This is a finite set of numbers, so whatever the sup is, it's the equivalent of the set maximum. However, the sup norm also exists for vectors where there are not just a finite number of coordinates. We'll actually have an example of that in this lecture. So while I could have written maximum here, sup is the broader expression, and this is called the sup norm because we can apply this in other contexts. All right. Again, it's not clear at the moment why this fits in with the others, but I have a little exercise for us to look at. Here's an exercise for us to test our understanding of the LP norm. We are going to work on the vector space R2. So for me, that's like the board I'm writing on. For you, you can think of it like your piece of paper. I would like for us to create some of the unit circles for these different LP norms. So first, what do I mean by unit circle? What is a circle? A circle is a set of objects which are the same fixed distance from a point, a center point. Okay, so translating that notion to a unit circle in a normed vector space, the center is going to be the origin. And in this lesson, we're not really thinking about distance, we're thinking about length or size or norm of objects. So to translate this idea of elements being a set distance away from the origin, we're going to say that that is like find all of the vectors in the vector space whose size is 1. So here I'm looking for vectors for us from R2 whose size with respect to the relevant LP norm is 1. So the set of vectors that satisfy this statement will be the unit circle in this normed vector space. Okay, I wrote x here, vector x, but since we're working in R2, I think it might be worth writing down what the LP norms can look like for this one particular example, instead of working in generality for this illustration. So in particular, I can think of my vectors as just xy pairs. We're going to take their LP norms, which is going to be take the size of x, raise it to the pth power, take the size of y, raise that to the pth power, add those together, and then raise that sum to the 1 over p. Okay, so that kind of gets rid of all of the extra dots and things like that. All right, I would like for you to do each of the circles I'm going to mention on your own, but before I turn you loose on the L1 unit circle, let's write down this expression again for the L1 norm. So that's going to be the L1 norm of the pair xy is just the absolute value of x plus the absolute value of y. Okay, on your own now, so pause this. Try to identify all of the points in the xy plane, so all of the points in R2, whose sum written this way. So the absolute value of the x coordinate plus the absolute value of the y coordinate is equal to 1. Okay, let's see how you did. Hopefully your unit circle in R2 with respect to the L1 norm or the taxicab norm, hopefully it has a distinctive shape. So it shouldn't look shapeless like some blob or something. All right, a couple different ways you could attack this problem, including numerically with MATLAB, which is what I will do in a moment. But let's start by just naively grabbing some points that we know will work. So we are looking for all pairings of x and y so that the absolute value of x plus the absolute value of y is 1. Okay, so the easiest points to recognize are combinations of 1 plus 0 and 0 plus 1. That gives us 4 points along the axes. So x is either plus minus 1 or y is plus minus 1. Like that. Then you could just start coming up with other sums that would work, like 0.5, 0.5 plus minus either coordinate, right? Because we have absolute values here, so both positive, x negative, both negative, only y negative. Okay, you would get that, and at that point, you might have been done. Or you could do like 1.75, 0.25, etc. If just grabbing combinations that work and then adding points to your graph didn't feel quite right, what you could do is think of this as 4 different line segments. Let me put it in traditional like slope intercept form. I think you could just work with this and back out the 4 line segments that way, or you could say, well, this is like the absolute value of y is -1 times the absolute value of x plus 1. Because of the sign choice that we have when we look at the xy coordinates that we're plugging into these absolute value functions, we're actually going to get 4 line segments out of this. So just first drop the absolute values. Imagine x and y are both positive. In the first quadrant, we would be looking at the line y equals negative x plus 1. So that's going to be y-intercept 1, slope -1, like that. In the second quadrant, where x is negative, absolute value of x is like negating x because x is negative. So this here in the second quadrant, what we call absolute value of x would just turn into negative x. But in the second quadrant, this would just be y. So we would have the line y equals negative negative x, so positive x plus 1. So that's y-intercept 1, slope 1. And we could keep going with the third and fourth quadrant, similar analysis of these absolute values, depending on the signs of x and y, or we could just realize, hey, this is going to be rotationally symmetric in the third and fourth quadrants. Okay, so there is our diamond-shaped unit circle with the taxicab norm. I don't know why I want to fix this, but okay, there we go. All right, so it is a diamond shape. Yes, it's also a square shape if you tilt your head. I want to call it a diamond for one particular reason. If you say square, I don't picture this. If you say diamond, I picture this. So I would like to keep calling this a diamond. With respect to this taxicab norm in general, circles, what we call circles, are diamonds. So if I say, what is the circle about the origin of radius 2 with respect to the taxicab norm, it's going to be just a larger looking diamond shape. So that's the idea here, is that with this other norm, we can create geometric ideas like circles. They might look different though. Okay, the L2 unit circle. Hopefully you didn't spend too much time on that. That is just the unit circle. So that's a familiar unit circle. Let's go through the soup norm unit circle. So I'm going to pause for a moment, erase this, and then we will look at creating the unit circle with respect to the soup norm. Then I will put up a little movie illustrating a whole bunch of these norms. To figure out the unit circle with respect to the soup norm, we want to find all of the points in R2 so that the soup, or the max, of the size of their two coordinates is exactly 1. Okay, so again, really, this is just saying maximum here because this is a 2-element set. All right. This one is actually pretty quick once you realize what's going on. This is a 2-element set, and we want the soup to be exactly 1. So let's start with when x is 1. If x provides the soup, that means that the second number cannot be larger than 1. So let's say x is 1. The size of the y-coordinate can't be larger than 1 because then it would be the set supremum, and that would be a bigger number than 1. So it's everything between -1 and 1. So let's say when x is 1, the y-coordinate can be any value between -1 down here and 1. That's not the only way for the supremum to come from the x-coordinate. It could have also been -1. And then same story for the y-coordinate. If this was the set supremum of 1, this would be between -1 and 1. So we have this shape. A square, right? So that's one reason why I want to call the taxicab unit circle a diamond, just to make it look different from this square shape, which I think is like a very good looking square. Let's picture the other norms that we've seen, the L1 and the L2 norm on this picture, this hand-drawn picture. Then I'll put up a MATLAB movie. All right, so for L1, the taxicab unit circle, what we had were these straight line segments connecting the intercepts. Like that. For the L2 norm, just the unit circle. It's a circle, so I'm not going to draw it quite so well, but it's going to be the circle of radius 1. So that's pretty okay. Okay, so we've got L1, L2, L infinity, the soup norm. Notice how they're nested, right? This is just 3 examples from this family. Let me step aside now and put up a MATLAB movie I made showing you all of the L1 norms. Not all of them, because there are infinitely many, but I'll show you enough so you can kind of see what's happening as we go from the L1 unit circle out to the soup norm unit circle. I hope you enjoyed that illustration. Just for fun, because I have the movie ready to go, let's head the other direction with the value of p. I'm going to start with p equals 2 so that we're looking at the nice classic unit circle, and I will decrease p down to 0.1. One neat thing we noticed with the first MATLAB movie is that for larger and larger values of p, our notion of the unit circle looked more and more like the square that we associate with the soup norm circle, unit circle with respect to the soup norm. That leads us to the following remark, and I really enjoy this proof. So we are going to show that as p goes to infinity, the LP norm looks more and more like the soup norm. So in particular, those unit circles are going to kind of converge on that square, which is the unit circle with respect to the soup norm. I like this exercise because it recalls an earlier pair of estimates that we did, where we said that if a vector is bounded by a certain number, then each of the coordinates are bounded. And likewise, if the coordinates are bounded, you can give a bound on the vectors. This exercise is going to be very similar, except for there, we were talking about the L2 norm. So we were working in Euclidean space, and here we're going to be working with just LP norms. What I'm going to do is take a specific vector x, which shouldn't be 0. So let's prove this by saying, suppose x is non-zero, and let me go ahead and say that the jth coordinate of x using our standard notation is the one that has the max size. So it's going to be the one that gives us the supremum of that set of coordinate sizes. What I'm trying to say is, and suppose that the size of the jth coordinate is the soup norm of x. So it's the soup of this set. I don't know which coordinate the jth coordinate is. I'm just going to kind of imagine it as in the middle of the vector. And it is not required that this coordinate be unique. So it's possible that the vector x is the vector 5, 5, 5, in which case all 3 coordinates satisfy this statement, and that's okay too. Notice, going to have a chain of inequalities here. Going to start with the soup norm of x. Let's see if we can fit this all on one screen. So how about, I'll start here. The soup norm of x is this number, which I'm going to, in the interest of space, actually, let me just work to the right in the interest of space. This is literally the absolute value of x to the j, x sub j to the p to the 1 over p. This recalls an observation I made in that earlier exercise, which is that the absolute value of a number can always be written as the square root of that number squared. Here's the same statement. Now, to this 1 over p root that we're taking, I can add in non-negative terms, and if anything, we go up in size. So we're going to say that this quantity is less than or equal to the size of the first coordinate to the pth power. So this is a non-negative number. Add all of those in, keep this. Okay. So this part is what we're repeating to the 1 over pth power on the outside. And then I've added into this expression a bunch of non-negative terms so that if anything, we go up in size. Again, in the interest of space, let me write to the right here that this is the LP norm of x. I didn't really specify what p is here. Sometimes you start to write a proof and you realize, oh, I need to add a little extra phrase into my preamble. Let me pause now and let you kind of reorganize your proof if you like, and then I will continue this computation. Let's just keep going. I'm going to go up in size now from this to create an upper bound on this LP norm, also in terms eventually of the soup norm. So we're going to now go larger than this expression and see if we can get back to the soup norm somehow. Okay. There's like not much to do. I mean, here is the LP norm. To get to this point, we brought terms in, right? So I started with only this and I brought stuff in. Now what can we do? Do we have any options here? And I think the only thing that comes to mind is to take all of these terms that we brought in. They started as zeros. So all of these expressions in here, They were just plain old 0 here. So we went from 0 to something. That's why we went up in size. We want to go up in size again. What could we go up to from these terms? Like, is there a top to this expression? And the only good candidate is x sub j, the size of that raised to the p. So it's like, I want to raise them to something. And this is the only really valid thing to do, is to go through now and take all of these potentially smaller expressions. They don't have to be strictly smaller than x sub j, but they're certainly not larger. And if anything, increase them as needed to get from whatever they currently are up to the set supremum, which is the size of x sub j. So x1, the size of x1 to the p is going to turn into the size of xj to the p. Just make all of those conversions. This one doesn't change. Okay. If I did anything to the coordinates, I increase them. The size of that to the p is going to be larger. But now this is nice because I can literally add these together. It's in copies of the size of x sub j to the p. So this is in copies of this. But now we realize that we just have a product here being exponentiated. So this is going to be, let me start here. The size of x sub j to the p to the 1 over p is just the size of x sub j. Okay, I'm going to write, I was trying to think about space. Okay, so the size of x sub j times n to the 1 over p. N is not a variable here. N is the dimension of the space we're working in. So we're working in Rn. So n here is like a fixed number. In R2, it was just 2. Okay, if you have the exercise that we did relating bounds on vectors and coordinates in Euclidean space with the L2 norm, when p equals 2, we had two statements. One of them we already brought in here, basically, where we said the size of any coordinate is less than or equal to the size of the vector. That was all Euclidean notion of size. Then we said if all of the coordinates are bounded above by some number b, then the size of the vector is bounded above by b times the square root of n. And that's exactly what we're looking at, except here, instead of calling the square root, we're calling it into the 1 over p, because p is not necessarily 2. But it's the exact same statement and same computation. The bound b was a bound on all the coordinates, but notice the size of x sub j bounds all of the coordinates. All right, I have one more thing to write before I'm going to end up erasing this so that we can finish this exercise with the squeeze theorem. This, of course, is the sup norm of x times just this number. So whatever the dimension of the Euclidean space is, to the 1 over p power. All right, I'm going to need to erase this, but we're almost done. All of this computation led to three things we want to relate. The sup norm of x, that's the smallest expression on this computation. The LP norm of x, and then the scaled version of the sup norm of x. So when I come back, we will have the sup norm of x is less than or equal to the LP norm of x, which is less than or equal to the sup norm of x times n to the 1 over p. We'll let p go to infinity to finish this problem. We want to take the limit of this middle term as p goes to infinity. We have it bounded on the left by something with no p dependence. On the right, as p goes to infinity, 1 over p goes to 0. So this is going to go to n to the 0, which is 1. Again, n is just the dimension of Rn. So there's nothing indeterminate about this expression. So I think we can go ahead and wrap this up, right? So by the squeeze theorem, the limit of the middle expression as p goes to infinity will be the sup norm of x. Because on the left, it's bounded below by the sup norm of x. On the right, it's bounded above by something which is going to the sup norm of x as p goes to infinity. So in the middle, we're being squeezed to the sup norm of x. Okay, so that wraps up this exercise. We've been looking at the sup norm on Euclidean space, where I kept writing sup, but it seemed like maybe I should have written max because we were taking the supremum of a finite set. Here's an example of the sup norm in a different context. So this is defined a little differently, but it's such a similar notion that we want to call this the sup norm as well. So in this context, we're not going to be looking at Rn. Instead, let's let M be the set of all bounded real valued functions on the closed interval from 0 to 1. So this is functions like f of x equals x squared, or it could be f of x has like a jump discontinuity. It's 1 between x equals 0 and x equals a half, and 10 from x equals a half to x equals 1. Whatever. They don't have to be continuous, but they do have to be bounded, and they have to exist for every input between 0 and 1. Okay, anyway, so that's M. The sup norm on this vector space, that terminology we will check out loud in a moment, is going to be defined as the sup norm of f. So here our notion of vector is a function. Well, consider all of the outputs of the function f, take the size of each output. So that's like, what is the absolute value of f of x for each x in the domain? Take the supremum of that set. The ultimate question we want to answer is this sup norm a valid norm on M? But before we get into the norm itself, let's talk more about M. We want M to be a vector space. Typically, checking that something is a vector space on paper, if this were an assignment, would be like check 8 things. Let me just do this casually out loud. So we need to check, is vector addition nice and is scalar multiplication nice? All right, so the vectors here are functions. If you take two bounded real valued functions, f and g, which are defined on the closed interval from 0 to 1, so is their sum. Their sum, f plus g, is also bounded, and it is also going to be a nice real valued function from 0 to 1. Addition is commutative. F plus g is g plus f. It's associative. F plus g plus h is the same thing as f plus g plus h. I was trying to remember where I put the parentheses in my speaking. The 0 element is in this set, so that's important. We have an origin. That would be the constant function f of x equals 0. And every function has its additive inverse. So if the function f is a bounded real valued function on this domain, so is the function negative f, so that f plus negative f is 0. Okay, so the vector addition is nice. Scaling is also nice. If you take a bounded function f and scale it by doing 3f, that's also going to be a bounded real valued function on this domain. And the scalar multiplication is nice. It's associative. The element 1 behaves appropriately. Okay, so that was just kind of an out loud check that M is a vector space, highlighting the main ideas of what it is to be a vector space. Vector addition is nice. Scalar multiplication is nice. Does this construction even exist? So if I say, hey, here's the sup norm of any vector from this vector space, is this even a well-defined computation? And the answer is yes, because if f is bounded, the absolute value of f is bounded. So this is going to be a bounded set, which means it has a set supremum. So any vector from this set can be evaluated with this proposal for the sup norm. Okay, so we have a vector space. We have a function on that vector space, which makes sense. It's defined for any vector from the vector space. Now we need to check the 4 properties. So we have like the first sentence of our definition of a norm. We have 4 properties to check. Take a moment, pause this video. If nothing else, just say the names of the 4 properties out loud. So see if you can name each one of them. Go ahead, check them if you like. And then I will come back. We will do a pretty quick evaluation. I don't want to go too into detail because we've seen this before. And also we have one more exercise to finish this lesson. The 4 properties we need to check are positivity, non-degeneracy, multiplicativity, and the triangle inequality. So if you can name them, that at least is a good start. I'm going to write out each one, but in the interest of space, I'm not going to keep writing out this expression. So I might write sup of the absolute value of f, and I'm not going to keep rewriting the domain. Okay, so let's start with positivity. We want to check that the sup norm of f is non-negative. It's pretty straightforward. Notice the sup norm of f, which let me write what that is. It's the sup of the set of outputs, sorry, the size of the outputs. And this is greater than or equal to, how about just the size of f of 0, which is, sorry, greater than or equal to 0. All right. The idea here is that the sup norm value is the supremum of all possible output sizes. So just pick one of those sizes. This is bigger, greater than or equal to. Okay, and then I know that this is just absolute value of a number, so this is non-negative. Okay, I think you followed me with that, so let's move on. The second one is non-degeneracy. That's an if and only if. Usually one direction is easier, and that's checking that the 0 element has a norm value of 0. First, observe that here when I say 0, I mean the function f of x equals 0. But that's the 0 function. Every output is 0. Maybe I'll write absolute value of 0, just to make it clear that this is the function itself. It's this is the function whose constant output is 0. And then this is literally 0. Okay. Take a moment to go the other direction. In most situations with non-degeneracy, checking the other direction takes a little bit more work. We want to check that if the sup norm is 0, then what we were taking the norm of was the 0 vector, the origin in the vector space. In that case, that's this constant function 0. Conversely, if the sup norm of some function is 0, then that means the set supremum was 0, which means each element of the set is less than or equal to 0 because each element of the set has to be less than or equal to the supremum. So then the absolute value of f of x is less than or equal to 0 for all x in the domain. But this is a non-negative quantity, which we're saying is less than or equal to 0. That's only possible if it's literally 0. So f of x equals 0. Sorry, the absolute value of f of x equals 0 for all x in the domain. So f of x is 0. Okay. Our next property is multiplicativity. With the next two exercises, what I'm going to do is work with the set supremum, assuming that we've covered that in Real Analysis 1. So notice alpha times f, the sup norm of that is going to be the supremum of the set of values that look like the absolute value of alpha times f of x for all x in the domain. But that's going to be the same thing as the supremum of the constant number absolute value of alpha times the size of f of x for all x in the domain, and then this comes out. Sorry, absolute value of f of x. There we go. Don't stop here. When you're verifying properties, take it to the very end, which in this case means taking the sup expression and replacing it back with the sup norm. So this is going to be the size of alpha times the sup norm of f. Okay, so don't cut it short. I'm going to erase these to finish with the triangle inequality. Okay, let's wrap up this triangle inequality pretty quickly. So I want to do the sup norm of f plus g. So that's going to be the sup of this set for each input x from the domain. This number is less than or equal to what I would get if I apply the triangle inequality to the absolute value expression in here. So the sup of this set is less than or equal to the sup of this set. So the absolute value of f of x plus the absolute value of g of x, because again, for each x from the domain, this number is less than or equal to this number. So this set supremum is less than or equal to this set supremum. And now again, with sup algebra from, say, Real Analysis 1, we break this up. Gonna wrap this up quickly. So soup, the size of G for all x in the domain. And again, don't stop here. Stop with the final statement, which is the soup norm of F plus the soup norm of G. Okay, so the soup norm of the sum is less than or equal to the sum of the soup norms. So we have the triangle inequality as well. Therefore, this is a valid normed vector space. That's what we actually wanted to show with this exercise. Sometimes you forget. All right, we have one more thing to look at. It's going to, on one hand, be another exercise in checking the four properties, but there's an important message with this final example. So please stick through to the very end. In the last lecture, we looked at inner product spaces. This result tells us that if you have a real inner product space, then automatically you inherit a norm. So we can say the inner product induces a norm. Here's what that norm looks like. So if you take a vector v from the vector space in question, the norm of v defined by the inner product is going to be the square root of the inner product of v with itself. So this actually matches how the Euclidean inner product induces the Euclidean norm. Here we're saying any real inner product space automatically admits this norm. So what we need to do is verify that this is a valid norm, which means check the four properties. And then anytime in the future that you recognize that the norm we're working with comes from a valid inner product, you don't have to check those four properties. So if we check them once when we prove this result, then we never ever need to verify again that a norm of this form has the four properties. It's going to be automatic because we're going to do the proof right now. Okay, so we know for free from the statement that we're working with a, a vector space, so there's nothing to check about the background set that we're working on. Let's verify quickly that this operation makes sense. From positivity, we know that the inner product of v with itself will not be negative. So we can compute the square root. That's all I needed to do. I just wanted to check that I wasn't going to be computing the square root of something negative and leaving, say, real numbers. Okay, once again, I want you to pause and, if nothing else, say the names of the four properties that we need to check out loud. If you'd like to, you can go ahead and check them on your own. I will check them all for you. And I think it's really worth watching. So if you're like, okay, the four properties again, I'm ready to stop watching this. No, please do watch this all the way through the end because I want to really highlight, especially with the first three properties, how much information the norm is getting from the inner product. So a lot of these verifications are super fast because we already know that we're working in this real inner product space. So it's like, I want to point out how much we inherit from the inner product. And then one of the tests is going to involve an identity that we met in the past. And I just want to point that out because it's nice to see that identity in action. All right, properties 1, 2, 3, we can check very quickly. And then the triangle inequality will probably need a blank space for that. But let's go ahead and I think I'll try to write this out with full sentences. So how about proof for any vectors v and w from the vector space? And when we do multiplicativity, we'll need that scalar alpha. So let me say alpha in R. Notice, okay, so it's just a nice opening sentence. Now we can do positivity. Let's see. What is the norm of V? The norm that we're proposing is to take the square root of the inner product of V with itself. And we're basically done because we are working with a valid inner product. So we don't need to check the properties of the inner product. We're told this is an inner product, which means all of those inner product properties that we visited in the last lesson come for free. So in particular, the inner product of V with itself must be greater than or equal to 0. So therefore, we're taking the square root of a non-negative expression, so the result will be a real number. That's really, so square root of anything that is going to be greater than or equal to 0. The question is it real or not? In this case, yes, we know it is. So let me just finish this by saying greater than or equal to 0 as VV. The inner product of V with itself is greater than or equal to 0. So this property of the norm is inherited from the positivity of the inner product. Likewise, let's look at non-degeneracy. In the past, when I checked non-degeneracy, I checked the two directions separately. So check that the norm of the 0 element is 0, and then conversely check that if the norm is 0, then the vector you plugged into the norm was the 0 vector. In part because that second direction usually needs a little bit more work. Here, things are going to come faster because we're working with an inner product that we know is valid. So let me write the norm of V is 0 if and only if. Now let's just say what the norm of V is. That was the square root of the inner product of V with itself. Oops. Okay. So here my if and only if is kind of like saying this is exactly that. All right. Square both sides, or just recognize that a square root of 0 is 0 if and only if the inside is 0. So how about this is if and only if the inner product of V with itself is 0. So the square root is 0 if and only if what you took the square root of was 0. That's just a fact about square roots. And now look at what we have. The inner product of V with itself is 0 if and only if V is 0. Because we already know that the inner product is non-degenerate. So I don't need to do both directions here separately because we already have this statement from the last lesson. So I'll just write a little note here that this if and only if proof was so easy compared to previous checks of non-degeneracy because we already know that the inner product is non-degenerate. For multiplicativity, let's take the vector v, scale it by this real number alpha, and compute the norm of that. Be careful not to look at this and just pull alpha out. We don't know yet that this is a valid norm. So even though we're using double norm bars, don't just pull this out. Okay, we have to go back to the definition of what we're claiming the norm should be. So I need to take this expression and compute the inner product of alpha v with itself, and then take the square root of that. Now we can bring these alphas in front of this inner product because of the multiplicativity of the inner product. So with each of these computations, it's important to notice where what we already have from the inner product comes into play. So here I can say that this is the square root of this alpha comes out and this alpha comes out, alpha squared times the inner product of v with itself. I could not do this if I didn't know that the inner product was multiplicative, but we do. We have an inner product space. And now the square root of a real number squared, as we've said a couple of times in this lecture and the previous few, is the absolute value of that number, times the square root of the inner product of v with itself. Don't stop there. Take it all the way through to that's the absolute value of alpha times what our norm of v should be. Like that. To check the triangle inequality, we want to see if the norm of v plus w is less than or equal to the norm of v plus the norm of w. It's a multi-line computation, and I don't want to write square root over and over and over again. So what I'm going to do is examine the norm of v plus w, that norm squared. Okay. That's going to be like squaring the right-hand side here. So that's going to be equal to, sorry, let me just rewrite that. The inner product of the sum v plus w with itself Okay, we have linearity of the inner product, symmetry of the inner product, etc. So I can expand this. And using all the properties of inner product, maybe not all of them, but using properties of the inner product, we get that this expression is equivalent to the inner product of v with itself plus twice the inner product of v and w. There you're going to have to use symmetry to justify that, plus the inner product of w with itself. In the interest of space, I'm going to make an adjustment on this line. This middle term here, the inner product of v with w, could be positive, it could be negative, it could be 0 if v and w are perpendicular elements in their space. So it could be positive, negative, or 0. This is non-negative, this is non-negative because of the positivity of the inner product. If I take this inner product here and enclose it in absolute values, then if it were already positive, I've made no change. If it were 0, I've made no change. If this inner product originally was negative, I have increased the size of our sum here, so we will go up in size. Okay, so this could have been a second line and a third line, but I'm just going to put that all together. Now we are looking at the size of the inner product of v with w. In our lesson on inner products, we proved Cauchy-Schwarz. The version of that I gave was, I'll just write it really quickly, it was the inner product of v with w squared is less than or equal to the inner product of v with itself times the inner product of w with itself. That was the version of Cauchy-Schwarz that we had last time. Now I'm going to take the square root of both sides. That preserves the direction of the inequality. I'll write two separate square roots, which is great because this left-hand side is exactly what we have in the middle here. So for the umpteenth time, the square root of a number squared is its absolute value. So that's what we have here. And then I'm going to be able now to take that expression here and replace it with inner product of v with itself, inner product of w with itself. That's what's going to allow us to break apart the fact that we've paired v with w. We want to have v's and w's so that ultimately we can get to the norm of v and the norm of w. Okay, so let's erase this. We're going to go up in size. So Cauchy-Schwarz is an inequality. Replace this middle term with these two expressions, and I think we would not bring in norms quite yet. So let's just stick with inner products for another line, and then we'll revert back to norms. Okay, so from Cauchy-Schwarz, this is less than or equal to the inner product of v with itself plus 2 times the square root of the inner product of v with itself times the square root of the inner product of w with itself. So here we had to use Cauchy-Schwarz. Okay, let's just take this line now and rewrite it, but in terms of norms. So this looks like the norm of v squared. This is the norm of v. This is the norm of w, except I forgot that. Norm of w, and this is the norm of w squared. And you might see the ending. So if you would like, you could pause right here and just take it through to the conclusion. I'll come back in a moment and finish this. Okay, where we left off is a quadratic that factors perfectly. So this right-hand side is now going to be the norm of v plus the norm of w, this quantity squared. Starting at the beginning, we have the left-hand side of the triangle inequality squared. So the norm of v plus w squared is less than or equal to the square of the norm of v plus the norm of w. So I think I can fit it in here if I write thus. Just take the square root of both sides and we are done. So the norm of v plus w is overall less than or equal to the norm of v plus the norm of w as desired. In the next lesson, we will look at metric spaces and define what a metric is, measuring essentially a notion of distance between elements in the metric space. We will have a result very similar to this one. So for the next lecture where we define metric spaces, have this result handy. And actually, as we work through an analogous result on metric spaces, we will need these properties of norms. So carry these properties forwards into our next lesson. Thank you for your attention.